Hello everybody, today we're going to talk about voltage regulators, chapter 17. It's the last chapter of the course. We end with voltage regulators. They're not too complicated, fortunately. Ideal power supply or voltage regulator would provide a constant output voltage under any load condition or any input voltage condition. For example, let's say you have a 5-volt output power supply, 5-volt output. You could load that with 1 ohm, or you could load it with a million ohms, a mega ohm, and it wouldn't matter. It'd still be 5 volts output, ideally. The same thing as, let's say that 5-volt output power supply has a 12-volt input. You could feed it with 7 volts on the input, or you could feed it with 107 volts on the input. It would still output 5 volts. It would be immune to input voltage permutations, okay? Well, real power supplies or real voltage regulators don't work that way. All right, they have limitations, and those two limitations are referred to as load regulation and line regulation. Okay, so over here on the right here we have for the load regulation, this is a no load situation, and then full load, the power supply output actually drops down a little bit, right? So line regulation refers to the input, basically how well the output voltage stays constant with a variable input voltage. So it's delta V out over delta V in times 100%. That's the line regulation formula. You can also express it as V out per volt change of the V in percentage, and that's this formula down here, okay? We have load regulation, which is different. We'll do examples of these, I think, in a minute, but load regulation is different, where you have no load versus full load. So you take the no load voltage, which, let's say you use my 5-volt example. Say the no load voltage is 5.1 volts, all right? The full load voltage, meaning the voltage that comes out of the power supply or the voltage regulator when it's at its specified full load current. Okay, let's say it's a 5-volt, 1 amp voltage regulator. So when drawing 1 amp out of the 5-volt voltage regulator, you're not going to get maybe 5 volts. Maybe you get 4.9 volts, or maybe you do get 5 volts, but under no load, you get a little higher than 5 volts. Okay, so you take the difference between those numbers and divide them by the full load voltage and times 100%, and that gets you your load regulation. Okay. Our bench power supplies are designed pretty good. They're good designs, and they have pretty good numbers, 0.01% for line regulation, 0.01% for load regulation for this bench type power supply. Another way to look at load regulation, all right, is to just kind of come to the realization that all power supplies, all power sources in the real world have this Thevenin output resistance. Right? There's some resistance in the output, and that forms a voltage divider between with the output resistance and the load resistor. Okay, so some of that voltage from the internal source, which is ideal in this case, is that voltage is dropped across that Thevenin voltage or Thevenin resistance, and so you get less voltage left over for the load. Okay, and that's expressed here, the simple voltage divider formula. Okay, and you can look at it as this way: R out over RFL times 100%. Okay. Here's a load regulation example. Okay. So if you have a power supply with an output resistance of 25 milliohms, not very much, full load current of a ½ amp at a 10 ohm load, what's the load regulation and what's the no load voltage? So the load regulation is going to be R out over the full load resistance times 100%, so you have 25 milliohms divided by 10 ohms times 100, that's 0.25%. That's okay, not very good, but it's okay. And what is your no load voltage? Well, it's going to come up a little bit because you divide it by this expression, so it's 5.013 volts. Not 5 volts, but a little higher, because it's not loaded, okay? So voltage regulators, how they're made, there's two different basic types, okay? One's a switching regulator, one's a linear regulator, okay? The linear regulators is what we're going to start with. Linear regulators are series regulators and shunt regulators. We don't really talk too much about shunt regulators. I'll put a slide or two up here. So they're not used very much, but series regulators are. All right, and series regulators. Sorry about these Batman-looking diagrams. These are the ones I found for this material. But basically, it's a non-inverting op-amp. See this op-amp right here? It's a non-inverting topology. You have the feedback coming through your feedback resistors, just like before. All right, to the negative or to the inverting input. This non-inverting input receives a reference voltage. All right, so this op-amp is going to do everything it possibly can to make this output, right, match the input. That's what it does with the feedback, with the negative feedback. Now we're using this transistor here, which is referred to as a control element. Actually, it's a pass transistor. We call it a pass transistor. This is what the op-amp turns on and off. I shouldn't say turn on and off, but causes to conduct or conduct more, conduct less, depending on what it needs to do in order to make these two inputs the same, right? So that's what an op-amp does. It tries to, with negative feedback, it tries to force the output to cause the two inputs to be the same through this feedback. So this is your reference voltage. It's a Zener diode, right? And so it's constant, relatively constant, with your input voltage. So the input voltage can change, but the Zener reference is going to stay the same, right? So as this input voltage changes, okay, this transistor is going to see that and raise this output a little bit, but it comes back through the feedback, and the feedback of the op-amp says, no, wait a minute, now I'm going to turn this transistor off a little bit to make sure that these two inputs maintain the same voltage. Okay, it's the same feedback mechanism that we've always had for these op-amps, for the non-inverting topology. Okay, so this transistor here is the control element. It's going to get a little warm if you, because it's always on, and not quite all the way on and not quite all the way off. It's somewhere in between. All right, but it can get kind of hot if there's a lot of current going through here. Okay, it's very common. It's a very common voltage regulator, but this particular one isn't current limited. Okay, in other words, if you short this output, this op-amp's going to do everything it possibly can to, it's going to turn that transistor on all the way because it's seeing zero voltage coming in on its inverting input, right? Because this output's shorted. Oops. So that's going to burn up that transistor possibly, okay? So what we do is we use a current limiter transistor here. So if you see a lot of current coming through this resistor here, R4, which is not a very big resistor, right? 1.4 ohms, for example, it's going to turn Q2 on here, which is going to pull base current away and start shutting down Q1. All right, so that's a current limiting technique. All right, let me go back to this slide, which is a little example of with some numbers. Okay, so the output voltage series circuit is V out is 1 plus R2 over R3 V ref. That is your standard non-inverting op-amp formula, right? R2 over R3 plus 1, same thing. Okay, and it's going to multiply this input voltage, which is V ref. The V ref is 3.9 volts. Okay, so the V out is going to be 1 plus 100K over 47K, that's what these resistors are, times 3.9 volts, which is 12.2 volts. That's what the output's going to be all the time. All right. This is 18 volts on the input, but it doesn't really matter. As long as you have enough voltage to supply the transistor and the whole circuit, your output's going to be 12.2 volts. Okay. Now, there's a certain power being dropped across this transistor. What is it? 18 volts minus 12.2 times 0.2 amps. This is what if you have a load current of 200 milliamps. And so it's 1.16 watts. Not too much, but it will get warm. So there's that current limiting. We could also do this fold back current limiting. It's a different technique, which uses a transistor connected up with this voltage divider. All right. And that works a little bit better because it causes this voltage across this resistor to drop a little bit, which turns this transistor off a little more effectively. It turns Q1 off a little more effectively. All right. Shunt regulators, I'm just going to gloss over this. Shunt regulators aren't used very much. The control element is in parallel with the output, so basically starves the output voltage and shunts it all to ground. Okay, this really is inefficient. Gets very hot. The only advantage is it does have inherent short circuit protection. Because if you do short this output, obviously there's nothing left to work with, and all that voltage is dropped across the R1 here. Okay, but we don't use shunt regulators very much. Don't see them. Okay, do see series regulators and these switching regulators. Switching regulators are very common. They're very efficient because they just turn on and off a field effect transistor, a FET. Okay, using a pulse width modulation scheme. So here's a variable pulse width oscillator, okay, which is controlled by this op amp. All right, this is the same feedback mechanism we had previously. Okay, this used to go to straight through to this transistor, right? Here's the reference voltage, same system, except instead of going to this pass transistor, all right, directly, it goes through a pulse width oscillator. And this pulse width oscillator is has a very duty cycle, all right, so that the duty cycle gets greater when necessary in order to provide more current to the output. All right, this transistor turns on or off 100%. It's not anywhere in between. And you know what that means? It means this transistor is not getting hot at all. Q1's not getting hot because it's on all the time or off all the time. Those are the two best cases for a transistor. One has no current, the other has no voltage across it. So the power dissipation in Q1 is very low. This is shown as a BJT. It's normally a FET. Okay. Now, we have this inductor and catch diode and capacitor, this LC filter basically here, which filters out the switching waveform from coming through the transistor. Okay, so it just takes a taste of Vn and dumps it into this capacitor, which causes a step down function of the switching regulator. So you could have, let's say, 12 volts out here and 5 volts out here. All right, all determines how you set up your pulse width modulator and your reference resistors here. All right, now this is really common. This is an extremely common circuit. Usually your switching regulators are used at the front end of a system, and your linear regulators, which we looked at previously, would be used locally and closer to your sub-circuits and so on. Okay, so on a circuit board, for example, you have a main switching regulator coming in, and then that would distribute an intermediate voltage rail to the rest of your circuit, and different parts of your circuit, like your Ethernet circuit maybe, or your microprocessor, or maybe some audio circuits, they would have separate series regulators to handle their voltage and current needs. Okay. But anyway, this is a step-down switching regulator, super common. There's step-down, step-up, inverting. This is a step-up regulator circuit. The inductor is over on this side, okay? And the step-up happens because the inductor is changing polarity and actually causing a step-up in voltage right here, okay? So you can actually have 5 volts in and 12 volts out. Now, you're not creating energy here. It's very similar to a transformer where you have less current available on the output. All right, so you might have 5 volts at 1 amp on the input and 12 volts at a half an amp on the output, or less than half an amp, all right, on the output. Notice the transistor here is in a shunt configuration. And we also have voltage inverters, so you can convert a positive voltage to a negative voltage. And it's very, very common, very handy for audio circuits where you need that negative rail. And this is how it's done in your power supply in your bench, for example, to get plus or minus 12 volts, okay? Okay, the inductor reverses polarity, and then here's a catch diode, which causes this, with the switching waveform, causes this capacitor here to charge negatively, okay? But notice the common element between all these, this op amp here, right? This op amp receives the reference voltage, okay? And also gets the feedback here from the voltage divider, okay? This one's opposite because it's an inversion circuit. Okay, integrated circuit voltage regulators. These are just single chips that do our voltage regulating. And the 7800 series is very common. These are fixed positive output voltage regulators. Usually 3 pins. They're always 3 pins. They have different cases. This is a D-pack, this is TO220. Notice the little flange here. This is for heat sinking. Okay, so you bolt this to a piece of metal, chassis, the side of the chassis, or maybe a big heat sink, okay? So the number at the end here refers to, end of the part number refers to the voltage output. So 7805 is a 5 volt output, 7806 is 6 volt output, and so on. You can get 7824, 24 volt output. Not very common. Usually most of them are just 7812, 7805 I use. Those are on 7815 sometimes, okay? So those are the linear regulators. These are not switching, these are linear series regulators, all right? You can also get the, yeah, as I said, these are the heat sink surfaces. Here's a schematic of one, so you have a positive input, positive output, ground, couple capacitors, capacitor on the input, capacitor on the output. These are usually electrolytic capacitors, maybe 10 microfarad, 100 microfarad, something like that. These improve, these capacitors improve the load regulation and line regulation, particularly when it comes to transients. So if you have a transient load change, like a motor kicking on, or a relay or a solenoid or something that requires a lot of current right away, it'll get that current coming out of the capacitor and not lessen the demand on the voltage regulator, improve your load regulation. Same for this capacitor for line regulation. If you have some funny stuff going on your input voltage, it will smooth those out and give the regulator a break, okay? And again, these are heat sink surfaces. 79 series regulators are negative series regulators, so you have a negative input, negative output. Same idea though, okay? The type number 7905 is minus 5 volts, 7912 minus 12 volts. Never heard of this, 7905.2. I didn't even know that existed. I've never heard of that before, but I guess since it's here, it exists. 7906 is a minus 6 volts, so it's negative input, negative output. So with the series regulators, okay, remember you can't do an inversion. You can only do that with a switching type, okay? So with the series regulators, it's positive in, positive out, always step down, all right? So this would be higher voltage. The input would be higher voltage than the output, always. Well, in the negative, I guess in the inversion case, you actually have a higher voltage on the output, but it's less negative, I should say. Okay, so you might have minus 10 volts here, minus 5 volts here. Okay, so it's a lower absolute value on the output with these series regulators. LM317 is a special linear regulator that's adjustable. Okay, so it has this feedback network here. All right, feedback resistors. Doesn't have a ground pin. That feedback comes right into instead of the ground pin. Excuse me. And there's a formula for it. So the V reference, usually 1.25 volts for the LM317, times this formula, plus this small error voltage. This is an adjustment voltage that comes in here. Usually we ignore this. Oops, sorry. Usually we ignore this 50 microamps times 2K. It doesn't really amount to much. So anyway, you got 1.25 times 1 plus 2K over 150, end up with 16.8 volts on the output. So the 317 is an adjustable voltage regulator. It can be, you know, anything you want, almost within the specifications. I encourage you to look some of these up on DigiKey. LM317, the 7905.2, which I might do because I've never seen it, and the 78 series. Look these up on DigiKey and, you know, have a look at their data sheets. Okay, to increase the power handle, the current capability of your linear regulators, you can put a pass transistor in there, excuse me, and you can actually drop some of the power or all the power across this external pass transistor. So this could be a giant transistor, something with a big TO3 case or something that's capable of many, many watts. All right, many watts. And you can do it using this circuit here. Here's a little circuit of a switching regulator that we've used at work. This is the LM2596. So this is a monolithic, it's got the switch on the inside, it's got the pulse width modulator on the inside, 40 volts on the input. Coming out here, we've got anything from 1.2 to 35 volts on the output, depending on how you set your feedback up here. Okay, but here's the main inductor, and here's the catch diode. It's a Schottky 5822, and here's the big electrolytic charge capacitor. Okay, that's used on the output. They've added another little LC filter here to reduce the ripple. It does say in the text that these are noisy. This one is a little noisy. It depends on the switching frequency. I think this one, is in the high tens of kilohertz range, but they make these in the hundreds of kilohertz range, and the ripple and the noise is almost non-existent. They're almost as quiet as linear regulators. So it used to be back in a long time ago, and for audio circuits, you didn't ever use a switching regulator. Well, now you almost always do because they're so quiet. Okay. Okay, so here's some key terms to finish up. A regulator's electronic circuit maintains a constant output voltage with changing input voltage or load current. Okay, we have line regulation and load regulation. Line regulation is the percentage change in output for a given change in input voltage. And load regulation is percentage change in output voltage for a given change in load current. Okay, and then we have our linear regulators and our switching regulators. A linear regulator is a voltage regulator in which control element operates in the linear region. So they get a little hot, you know, they're not very efficient. But they're usually used for very low current situations, okay, in the milliamps. And maybe approaching an amp, but not much more. Switching regulators, on the other hand, have the pass transistor, which is turned on all the way or off all the way using a pulse width modulation circuit, which gets its feedback in the same way as a linear regulator, only the pulse width modulation duty cycle is changed to maintain regulation. Okay, the switch pass element is turned all the way on or all the way off, so therefore it operates very efficiently. Okay, so that'll do it for voltage regulators. If you have any questions, please post them in the discussion area. Okay, thanks.